So what we have understood is that for torque we have two formulas. Torque is equals to the magnitude of torque is r perpendicular into F, and like we have F is equal to ma, so torque is equals to, so at the place of m I have I, moment of inertia, into angular acceleration. Now for angular displacement we have delta theta is equal to theta naught minus theta, and if theta naught is 0 then angular displacement is delta theta is equals to theta. How do we calculate this theta? So this way also can be calculated if it is given in this way. Otherwise theta is equals to length of the arc divided by the radius, and that we can put in the formula omega square is equals to omega naught square plus 2 alpha theta, and we can find the theta with this formula also. So students, our next topic is angular momentum, and I'm already telling you that we are taking all the cases, so all the formulas are true only when we have a fixed axis. So the formula that we are deriving, they are considering that, so this is assumption that we are taking that axis of rotation is fixed. Okay, so now again starting with a typical particle which is typical particle of the rigid body which is rotating. Now which figure we are going to take? So here we will be taking angular velocity, linear velocity, momentum. So we will go back to figure 7.17b. okay, so open your NCERT books and you will see the figure 7.17b. So that's your figure 7.17b. Now of course we have a rotating body, okay, and the typical particle that we are taking, typical means any particle, okay, randomly chosen particle, that's the meaning of typical, randomly chosen. So for a typical particle, so of course this particle is of the rotating rigid body, what will be its what will be the angular momentum? So angular momentum, you know, we write with small l for a particle and capital L for the system. So that will be given, you know, the formula, the cross product r cross p. Now what's your r here? R is a position vector to this point p, so that's your vector r, the position vector, that is your OP. So position vector OP. How you will be writing OP? So OP, that's your OP, and I can write it as OC plus Cp. Okay, so that's triangular law of addition, OC plus Cp. Now, so the value of R I have got. What about value of P? P is equals to, that is my linear momentum, that is equals to mass into velocity. And what is it? So that's equation 1, that's second, that's third. Now what's your V? Okay, so I was concerned about R, and then P, then what's this V? So I want to write L, but for that I need R and P. So R I have got, but P again I have velocity vector. So what is V? So V, you know that V is equals to omega cross R, and the magnitude of V is equals to omega R perpendicular. So that's the value of V. So V is equals to magnitude of this linear velocity. I can take it as V omega R. Okay. Now, from first putting this value one by one, let us put 2 and 3 in 1. So put second and third in first. We get, what do we get? We get L is equals to OC plus Cp cross M into MB, right? Now this can be now cross multiply. So distributive law, OC cross MB plus Cp cross MB. Okay. Now here I can write it as now what is this Cp and what's this V? And what's OC cross MV? So let us see, this is your OC, and this is the direction of velocity, which is tangential, right? So OC is along the z-axis, and this V is along, it's in the xy plane. So this V is in your xy plane, and this OC is along the z-axis. So what's the angle between OC and V? That's 90 degree, right? So let us write it OC cross MV plus Cp cross MB. So putting the values, Cp, what is Cp? Cp is your R perpendicular. R perpendicular means the distance between the axis of rotation and the point P, that is into consideration the particle at point P. So that I can write Cp can be written as R perpendicular into M into what is V? We have already written V is equals to omega into perpendicular. So that's omega into R perpendicular. Now these are the magnitudes I have written. I have written the magnitude of Cp. This is the magnitude of Cp. Then I have written M, and then I have written the magnitude of linear velocity. Now this is a vector, so we need to write cross product is a vector, so we need to write the direction also here. We cannot write simply the magnitude. So what's the angle? So and then sine theta. What is the angle between CP and V? So I've just discussed with you that okay, this CP is radial distance and V is tangential. So tangential and radial angle is 90 degree. So here sine 90 is equals to 1. Okay, and then what's the direction? So that will be the cross product. So the cross product A cross B, we have to write magnitude of A, then magnitude of B, then sine theta, and then direction of n cap. So n cap, you know that if this is A, this is B, then n cap is perpendicular to the plane containing vector A and vector B. Okay, so sine 90 is 1, and then you need to tell the direction by the unit vector. So perpendicular to the plane of CP and V. So CP and V both are in x. If we take them in xy plane, like x dash y dash, we take. So this is your suppose xy plane. We have taken it like this, or how have we taken this? This as y-axis, and this as a x-axis. So this can be taken as x dash y dash, right? So, but the z-axis is perpendicular to this plane. So what is the z-axis? Direction of z-axis is this vector, unit vector k cap. So we write here direction with k cap. So this cross product is along the z-axis with this much of magnitude. Okay. So students doing every step logically, step by step. Okay. And then now this angular momentum of the particle we are talking about. So clearly and this OC is along the z-axis and your V is along the x-axis. So definitely this is not along the z-axis. This is along the z-axis, but this is not along the z-axis because OC is already along the z-axis. So it's perpendicular to the plane, this resultant perpendicular to the plane containing vector. Let us see to it. So we can write this is along the z-axis. So it means L has two components. Okay, one is this component. We'll discuss this OC into MV, but this component is clearly along the z-axis. Okay, and that is the so where LZ along the z-axis, so that's equals to, or you can write the magnitude of it because so that is what is the magnitude? So mass and then r perpendicular square and then omega. So that's your LZ. Okay. Now if you want to find the total momentum, total angular momentum of the body, now total angular momentum, yes, angular momentum, capital L, of the whole rigid body is, so how will you write it? Like summation of Li, one of the typical particle you have taken, and that will be equals to, so this and this. I will be taking the summation of let us write Lz first. So Lz summation plus summation sigma OCI cross MI VI. So as this component is perpendicular to the z-axis, I have discussed with you because OC its direction is along x-axis, I discussed, and this OC is along the y-axis. See, OC is along the axis of rotation. That's your z-axis. Okay, so OC is along z-axis, and the direction of this V is tangential, so it keeps on changing the direction of VI. So that's fixed. It's fixed, but the direction of VI, it's keep on changing. It's tangential, right? So the direction of VI keeps on changing. So now the point here is that our cross product, like I was writing A cross B, so that's A B sine theta into n cap. So students, this n cap, this direction is perpendicular to vector A, this direction is perpendicular to vector B, and this direction is perpendicular to the plane containing A and B. So understand these 3 points. Okay, so if this is total angular momentum will also have 2 components. That's equals to this, the first component, capital LZ, plus this second component. So this is along the z-axis, and you can clearly see that this OC is along z-axis. So this cross product will definitely be perpendicular to z-axis. Okay, like the resultant vector is perpendicular to vector A and perpendicular to vector B. So this n is along z-axis, and A and B are in xy plane. So definitely this vector is going to be perpendicular to the z-axis. Okay, so hence this angular momentum will have 2 components, one along z-axis and second one perpendicular to this component which is along z-axis. Okay, so you can write that L has 2 components, LZ, first one is LZ parallel to z-axis. Okay, write it like this also, that doesn't matter. And second one is your L perpendicular, that is perpendicular to z-axis. So now let us calculate LZ. Let us find LZ. So LZ, you know how we can write it down. Sigma, this is sigma. It's better if I write here LIZ. Okay, sigma LIZ. This is what LZ is, and that's equals to, now what's the value of Li? So Li will be equals to sigma Mi Ri Liz is over here, so we can name this equation as equation 4. This is my this one is this one is equation number 4, this equation, and that's, students, your LIZ. Yes, remember this from here. So let us write this value from here. So that's your value of LZ. So what is it? Yes, this is from where we have written this LZ. This LZ, yes, this is the same one. Okay, so what is LZ? So that's equals to sigma, so summation mi, and further it is written as LZ. Okay, so that's what LZ is. So you can write this one as equation 5. So it's where LZ is equals to this. So mi are perpendicular I, so this is perpendicular distance. Okay, or perpendicular I you can write into omega, and you know omega is constant, so you can write omega either here, or you can also write the omega over here also. Put a bracket over here. So constant values comes out of this summation sigma sign, and so that's the magnitude of LZ. Now here it is vector, so what's the direction? So direction is along the Z axis. Okay, so using 5. So I hope you are writing along with me. That is why I am so slow, and hope you are understanding it also properly. Now, what is this MIRI? So MIRI is your moment of inertia. So LZ is equals to the summation RI, summation MIRI is your moment of inertia of the body, into omega into its direction, kk. Okay, and now what about I and omega? So along a particular axis, moment of inertia of a particular body is constant, right? And angular velocity, we know that it's constant over here. So basically LZ is constant. So LZ, that's equals to I omega, is equals to constant. So that's very important concept, students. That's important derivation. Okay, so what is the significance of this LZ is equals to I omega constant? So that's if you look at it, what is the implication of L being constant? So when do we have L constant? You know the formula that dl by dt dp by dt is equals to force, and dl by dt is your torque. So L is constant. So L is constant if can only be if tau is equals to 0. So if tau is equals to 0, then only L is constant, because derivative of a constant is 0. Okay, so we have used it earlier also, and it means L is I omega, and that is constant. Okay, so that's so we are considering LZ as 0. Okay, we are considering LZ as 0, so we'll derive it, we'll write it down. So that's my law of conservation of angular momentum for symmetric bodies. This is the law. But we are considering here the total momentum as LZ. It means I am considering this L perpendicular as 0. So let us find out whether it is 0 or not. So now our target is to find, let us find the second component, that is L perpendicular to z-axis, this component of angular momentum of the body. So now we are considering the rigid body. This law also comes later, okay, after this discussion. So now we are considering a special case in which the rigid body is symmetric about axis of rotation. So consider the rigid body. So this can only be possible if the rigid body is symmetric, okay? And where it is symmetric? Rigid body, consider rigid body is symmetric about axis of rotation. Or you can say means one of the symmetric axes you can take. Means the rigid body is rotating about one of the symmetric axes. Okay? So it's plural here, AX, ES. Okay? One of the plural word here. Okay, so for such a body which is symmetric about the axis of rotation, so for such a body, OCI, what will be your OCI? Because L perpendicular is your OCI cross MIVI. What is this LZ? That's your OCI cross MIVI, right? This is what your LZ component is. Yes, from here this we can write it as equation number 6. So from 6, okay, so that's your L perpendicular. And now we need to do summation of it. For if we are writing it for the body, that is for the particle, and summation then it will be for the body. So writing it for the body, summation over here. So you know that your OC was here along the z-axis, and this V is the direction of V was tangential to this. So this was your V and this is your OC, right? Remember direction? So that's along z-axis. Now for such a body which is symmetric about this axis of rotation, definitely if you have some particle over here whose velocity is v, you will find because it is symmetric body, so you will find a particle in the same position on the other side whose velocity will be v, right? So you will have if there is one component of vi, you will have another component of minus vi. So for such a body which is symmetric which is rotating about one of the symmetric bodies. So for such a body, students, this is a very important discussion. For a given, these are one of the tools of doing the calculations, doing derivations in physics. So for such a body, for given OCI, for every particle with linear velocity vi, there is another particle with linear velocity minus vi, isn't it? If this you are considering as plus vi, this will be considering as, this you can write it as minus vi. Agreed? So what will be the result? When you are doing the summation L perpendicular, which is equals to summation OCI cross MI VI, so one component you will be getting as positive and another component you will be getting as negative, so they will be cancelling out, and as a result you get LZ is equals to 0. So now this LZ is equals to 0, but there is a condition. It is only for symmetric bodies. So bodies which are symmetrical, okay, so bodies rotating about symmetric axis. So axis is symmetric, means the, so you can write that's the same thing, rigid body rotating about the axis of rotation, or this. So how do we have this kind of symmetric body? Like your body is a symmetric body, and like acrobat is means on the floor is, you know, a dance performer or acrobat, they are, you know, spinning on their toes. So some of the time they are folding their hands, and then they are you know, unfold their hands to increase or decrease their angular velocity. Okay, so that's the concept that is important, that we are going to do. So that's we can consider this as equation number 7. Now where we were, so we were over here, equation number 6. We have calculated this component Lz as I omega, and we have calculated this as 0. So this quantity I discussed with you that this will only be this possible when this component will be 0. So we have found the L perpendicular is 0 when the body is symmetric and rotating about the symmetric axis. So this L perpendicular, this component is 0, right? So we are left with only Lz, and that's the value of Lz I omega, right? So putting these values, so this is actually equation number 7, and this we can write at equation number 8. So put 7 and 8 in 6. Okay, so what do we get? So L, what was your value of L? So L was your Lz plus L perpendicular to z axis, and that we have found Lz is equals to I omega. And what is the direction? And that is along the z axis. So it is clearly written over along the z axis. So this L is equals to I omega plus what is L perpendicular? So L perpendicular is 0. Okay. Got it? Now, but again I'm rewriting it again and again for symmetric bodies, for bodies rotating about a symmetric axis. So that's the assumption, a special case we have taken. Okay, so here it will comes out at the L is equals to I omega, and I have discussed with you that case. So that's for the symmetric bodies, and that's constant. Okay, so now let us derivate this equation both sides. Now this L omega is constant, and that I told you that this is now after writing this, now write this thing. This thing is supposed to be written over here. I have discussed it earlier with a presupposition that Lz will be 0. So I have proved that Lz is 0. Okay, so this I have written assuming Lz as 0, and I have proved Lz as 0. So L is equals to I omega. Now you can write this that if the torque applied on it is 0, then L is constant. So this is constant if torque applied on it is 0. The torque is 0, then this L omega is constant, and this is the law of conservation of momentum. What is the law? If torque is equals to 0, then L, this is constant. This is the law of conservation of angular momentum for symmetric bodies. Why this is so? Because we know that tau is equals to dl by dt. So if tau is 0, L is constant, and L is equals to I omega. I omega is constant. So students, what does this mean? This means that so like I discussed with you, that you can see a figure in your book also. That is figure 7.36a. So figure 7.36a. Page number 173. So this is a demonstration of a girl, demonstration of conservation of angular momentum. Here we have a girl that sits on the chair, and it's wheelchair. So you can see that let me bring this figure on the board. So this chair has wheels at the bottom, okay? And this girl stretches her arms and or bringing her arms closer to the body. So either stretching the arms or bringing the arms near to the body. So students, okay. Very important concept, law of conservation of angular momentum. So now when she is sitting on this rotating chair and spreading her arms horizontally, what about her angular speed? So stretching the arms, okay? There are only two positions. One is stretching the arms, right? And second is folding the arms or bringing arms near to the body. So two positions only. So how is it impacting this L? So in both the position we can see that there is rotation about the symmetric axis. So in both the position L is constant. So what are the conditions that we need for this law of conservation? What are the two suppositions? First, students, first supposition is that this L can only be constant in these two positions. First thing is that there is no external force applied on the body. Nobody is touching this girl, and we are considering the air resistance as 0. So this is the first thing, that tau is equals to 0 here. Okay, and what is the second condition? Second condition here is the rotation about symmetric axis. So when you have these two things, okay, so this implies that L is constant, angular momentum is constant. So angular momentum is constant means I cross omega is equals to constant. So stretching the arm, what will happen if you stretch the arms? If you stretch the arms, you know that this mass is going away from the axis, right? And you know the moment of inertia, that is sigma mi ri square. So directly proportional to the square of the distance from this axis of rotation. So if you are increasing this distance, you are increasing, mass is constant, but you are increasing this ri distance from this axis. So if you are increasing this distance, moment of inertia will increase. So stretching the arm means you are increasing the moment of inertia, but I omega is constant. So if you are increasing I, so if suppose here I have 6 multiply, or you can write 2 multiply 6 is equal 2 multiply 6 is equals to 12. So this 12 is constant, but you are increasing I. So if you are increasing I, so definitely this omega will decrease. So increasing the I, so when you stretch the arms, the angular speed will decrease, okay, and as you bringing the arms near to your body, so this Ri will decrease, and as a result moment of inertia will be lesser. See, when is it easy to rotate a body? When when the mass is more spread or when the mass is less spread near to the axis. So when the mass is more near to the axis, you have lesser moment of inertia, that we did also when we were discussing the table 7.1. So here in this case, when the arms are near to the body, moment of inertia is lesser and the angular speed. So now if you are further means decreasing this, so again the angular speed will increase. So this way you can increase or decrease your angular speed just by stretching the arms or bringing the arms near to the body, and that is the application of law of conservation of angular momentum. But understand these two conditions. These two conditions are supposed to be satisfied. So this is the situation. So if the friction of rotational mechanism is neglected, there is no rotational torque about the axis of rotation, and I omega is constant, and stretching the arms increases moment of inertia about the axis of rotation, and it is resulting in the decrease the angular speed omega. And bringing the arms closer to the body has an opposite effect. Okay, it has the opposite effect when you bring the arms closer to the body. Okay, circus acrobat, drivers, or skaters, classical Indian, Western dancers, so they take advantage of this law of conservation of angular momentum. Now we have one more formula we have derived, that is L is equals to I omega, and you can see that P is equals to mv in linear motion and in rotational motion. So instead of linear momentum we have the angular momentum, and instead of m I have moment of inertia, and instead of linear velocity I have angular velocity or angular speed. If it is linear speed, this angular speed. So this is the formula that we have derived. Okay, but condition for this formula is that the rotation is about the symmetric axis, and conditions for this to be constant, torque is supposed to be constant. Now let us derive one more formula, the last one in fact, and that one is like F is equals to ma. So here the equivalent in rotational motion, tau is equals to I alpha. Okay, let us derive this formula now. So we have Lz, total momentum now, where that is your Lz, because L perpendicular is 0 about the symmetric axis, and that is equals to I omega k, right? So that's for the symmetric bodies. Okay, now differentiating it both sides with respect to t, what do we get? dl by dt is equal to, of course I need torque. So torque how will I get when this will be 0? So in fact I have done it earlier also, means this law of conservation of momentum, but let us derive it here in again a formal way. So that's your differentiating both sides. Now so of course d by dt of L perpendicular is 0 here. So as if L perpendicular is constant, if this vector is constant, this will be 0, and we are left with only the z component. And now here what's your dl by dt? So dl by dt is tau. So we are taking vector here. So when we are differentiating this, so you are not differentiating the magnitude, you are differentiating the vector. So we need to write here the direction also, students. So just be particular about it. Okay, so direction is along the z-axis, so same direction as L. So L is along z-axis, so torque is also along the z-axis. So magnitude and direction, and then I is constant, will come outside, and then this d omega by dt. Okay, and that's equals to tau is equals to I into this d omega by dt is alpha. So both are along the same direction, so this is the magnitude. So that's my ultimate equation. So here I have taken that this value dl by dt is equals to tau. So you can see that both are positive, so it means they are in same directions. So if their vector is equals to vector and there is same sign, so it means both have same direction. Okay, so that was your topic 7.13. Now we will have the last topic that we'll do tomorrow, that is 7.14. So students, tomorrow the class will I will tell you the timings. Thank you for being with me. Thank you, students.